So we need to start by looking at the nodes first. So we have 3 external nodes and 2 internal nodes. These ones, they're internal because they have members converging or diverging into these specific points. So what do we need to do with these internal nodes? Well, the moment distribution method tells us we need to artificially clamp them. So remember, AD looks like this. It will have a clamped end as well. Remember DB like this. Remember DE and remember EC. We want to clamp them to prevent any nodal rotations. So at these points we would have had nodal rotations. And we are only going to look at the rotations, the moments, due to these artificially clamped ends. So once you then release these artificially clamped ends, the node will be free to rotate. So if it's rotating, it has a moment. And the moment with which it initially starts to rotate has the same value as the moment due to the artificially clamped ends we have here. Eventually, the node is going to stop rotating because it gets into equilibrium, so it's going to have a value of 0. But that happens slowly, and that's where the iterative process comes in. This will make more sense by the end of the video. Okay, so let's write in the nodes in our table first. We said we have internal node D and E, and D is made up of members DA, DB, and DE. And node E is made up of members ED and EC. We also have node A, only made up of member AD. Node C, only made up of member CE. We also have node B. So what are we going to do with this one? Well, it's a pinned end. And we know that at pinned ends, the moment is 0. So no need to include it in our table because we're looking at moments, and node B doesn't have any value of moment to include. Okay, next up is the distribution factors and member distribution factors. You can find these distribution factor for AD, for DB, for ED, and so on, as a fraction of the stiffness coefficient of each member, in this case, stiffness coefficient of member DA, over the total sum of the stiffness coefficients at that specific node. So DA, KDB, KDE. And you know how to calculate these. And eventually you're going to get this value of 0.453. 0.453 as the distribution factor for DA. Okay, you can do the same thing to find it for DB, and you get 0.12. And you could also do the same thing to find DE, but there's an easier way to do this because you know that at the node, the sum of the distribution factors from each member make up 100%. So basically they add up to 1. So you can just do 1 minus this value to find the n member distribution factor at DE to be equal to 0.427. You can do the same thing at node E. So distribution factor for ED, fraction of the stiffness coefficients, and you get 0.727. And now just subtracting this value from 1, you can get DE equals 0.273. Okay. What about A and C? We don't have any distribution factors for these because these are not split into any members that make up the node. It's just one member that makes up the node. So basically it would have been 1. I mean, they don't have distribution factors. Okay. So now for the n member moments. Any external moments? We have external moments acting between member D and E, and it's of the form of a uniformly distributed load. And to find n member moments due to uniformly distributed loads, you do WL squared over 12. So you're going to do the load W, which is 50, times by the length 12. 50 times by the length 12 squared over 12, you're going to get 50 times 12 squared over 12, 600. So n member moment for DE is 600, and n member moment for ED is also 600. External moments. Okay, but if you add these together, you're going to get a total value of moment for member DE of 1200, and we want it to equal 0 because it's in equilibrium. So one of these values of moments is going to be negative. So one n member moment either of DE, say, rotates clockwise and the other end anti-clockwise to make it 0. It could be vice versa, but when you look in the n member moment table, you see that usually going from left to right, so in this case from D to E, that's the one you assume to be negative. Okay, but also we need to look at the deflected shape of the beam DE. And the deflected shape is going to look something like this. So we have a rotation theta at D and rotation theta at E. The rotation at D is in the clockwise direction, usually assumed to be positive. And the rotation at node E is in the anti-clockwise direction, assumed to be negative. So let's write these here. D was positive clockwise, and E was negative anti-clockwise. This will come in handy later on. Okay, so now we have a value of moment and distribution factors with which we can distribute this moment into each member. Same goes at E. But let's look at D first. So, to find the percentage, the fraction, the decimal of moment that member DA gets, we're going to multiply the distribution factor of DA by the total value of moment. And you're going to get 271.8. For DB, the value of moment that gets distributed to member DB, just multiply by the distribution factor, and you're going to get 72. And same goes for DE. This multiplied by this, and you get 256.2. Okay. So, something else we need to do is remember that for n member moment DA, for example, half of the moment at DA will get carried over to AD because it's a pinned end. If it was because it's a fixed end. If it was a pinned end, so like at B, you wouldn't have any carryover moment. Only for fixed ends. That's where you have to distribute and carry over half of the moment. So half of this, when you carry it over to from DA over to AD, so from DA to AD, half of this is going to be 135.9. And now looking at DB, we don't have a fixed support. At B, we have a pinned support. So no carryover moment. Otherwise, we'd have had to draw an extra leg in our table for BD, but that's not the case. Okay, DE. Half of the moment at DE is going to get carried over to ED. So half of DE gets carried over to ED. Writing this here, we get 128.1. Okay, so now let's look at the column for E. We have this value of moment and this value of moment that we need to distribute into members ED and EC using the distribution factors. So the total sum of the moment we're going to be distributing is 728.1. So for ED, the value of moment that ED has is the distribution factor times by the moment we're distributing, and you're going to get minus 529.33, and multiply for EC the distribution factor by the value of moment we're distributing, minus 198.7.77. Okay, but why do these ones have minuses and these ones don't? Because the minus here comes from here. So whenever you want to balance something at E, when you're balancing moments at E in this row and this column, they're going to be negative. And why are these ones positive? Because whenever you're going to balance moments at D, they're going to be positive. So we're going to keep this pattern going. Okay. So once again, we have to carry over the moment from this side and this side. Half of the moment from ED gets carried over to DE. Half from ED carried over to ED. So that's going to be minus 24264.66, and half of this one gets carried over to EC. So EC half gets carried over to CE. EC half carried over to CE. And that's going to be 198.77 over 2, 99.39. Okay. Once again, in the column for D, we have a value of moment that we need to distribute using the distribution factors. So at D, for DA, multiply the distribution factor by the value of moment we're distributing, and you're going to get 119.89. Same thing for DB, and same thing for DE. And once again, we need to carry over half of the moment to each side. Remember at the beginning of the video, we artificially clamped these ends from the nodes. So that's why we carry over moments, even though you don't see the clamped end, it is clamped here, here, and here. And here, and here. So we have to carry over half of the moment. Okay, so carry over half, you get 59.95. Carry over half, you get 56.51. Now you have this value of moment you need to distribute using your distribution factors. So when you do moment times distribution factor, you're going to get this value of moment. When you do moment times distribution factor, you're going to get this value of moment at the member EC, and keep the pattern going. You can see, look at our numbers, they're quite big to begin with, but they're getting smaller and smaller and smaller. This is the iterative process. And eventually they're going to become 0, And to find the total value at the specific point of moment, so for example, for A, you just add up all the carryover moments, and that's your total value of moment at node A, for example. And